Is it more the same?
Yeah. But what's going to make this a little bit longer? We got to apply product rule, but what? Twice, right? We have f prime g plus f g prime here, and then we also have another set of product rule here. Okay, so this is the factored form, so I'm going to skip that part. This is going to be useful when we're trying to create a velocity sign line. But here's my product rule here to get to my acceleration. Yeah.
Why did you do a plus and a minus?
Because that minus is because of this right here. It's the operation. Oh yeah, it should be just a minus here. Yeah, it should be a minus. Because of that minus, I have to make sure that after I go through product rule that I'm distributing that negative through, right? And I'm able to get my acceleration all the way down to e to the negative t times t squared minus 4t plus 2. All right, any questions so far?
Oh, Mr. Yang?
Yes.
Should there be a plus sign after 2e to the negative t?
Oh, you mean right here? Right here.
Yeah.
Well, the thing is that you see how these terms, there's a negative one here. I just pulled that negative one out in front.
Oh, okay.
And it just made it as a coefficient, so it made it a minus there.
Okay, thank you.
And then with the second pair be positive because the negative times a negative.
Second pair. Right here.
Yes.
That's right. So this one came out as negative. There's another negative there, so it becomes positive. Yeah. Okay, anything else? Okay, so then we're moving on to part B. So part B says determine the interval moving left. So if I want to find interval moving left, I have to create what? Yeah, let's create a velocity sign line. Okay, so velocity sign line means I have to find critical points. Critical points means set velocity equal to 0. So I think it's helpful, take our velocity function, get it into factored form. Or factor out. That way we can see all the necessary pieces that will build our, that we can use to find our critical points, which is when velocity is 0. Okay, so we set each piece equal to 0. On my key, I had it out of order here, so here's the work. Okay, so once I set my velocity equal to 0, the t is equal to 0, e to the negative t is equal to 0, 2 minus t is equal to 0. I'm only going to get critical point from t equals 0 and t equals 2. The e to the negative t, if I try to take natural log of both sides, I'm not going to get anything out of it, so there's no critical point there. Create my sign line. I know negatives are also values that I can include on my sign line, so I'm not going to have a starting point at 0. I'm also going to have points to the left of 0. So I'm going to choose 3 test points. I'll choose -1, I'll choose 1, and I'll choose 3. And each of them go into my velocity function. Remember that e raised to any power, no matter what, is always positive. So negative t, positive value, and then 2 minus a -1, that's positive. So I only have one negative here, so I know that I'm moving left here. Okay, plug 1 in, positive, positive, positive. Plug 3 in, I get positive, positive, negative. So I'm looking for negatives because I'm looking for particle moving left, -infinity to 0, and then from 2 to infinity. We don't include test numbers in our interval. Okay, any questions there?
Yeah, Mr. Yang, I have a question about something in part A.
Yeah.
So the second A of t that we have, the simplified one, I thought there was supposed to be a negative before the t squared e to the negative t, because there was a -1 there.
Oh, right here?
Yeah.
Yes, there's -1 here, but I'm also distributing a -1 through my parentheses.
Oh,
So
so they
these two
cancel out.
negatives will cancel out to be just positive.
Okay, that makes sense.
Okay, are we good with part B? Okay, part C, is the particle's velocity increasing or decreasing? How do we determine whether a particle's velocity is increasing or decreasing?
Plug it in and see if it's positive or negative.
Okay, is this talking about velocity though?
No, acceleration.
Yeah, it's talking about acceleration, right? You see the word velocity, but it's not the same thing as saying is particle's velocity positive or negative, right? If that was the case, then it'll be straightforward. Then you just plug in, find the velocity. But you see the word increase, decrease, that changes things. That's talking about the rate of change of velocity, and that's acceleration. So we just look at acceleration. So if acceleration is positive, my velocity is increasing. If acceleration is negative, then velocity is decreasing. So we plug 3 into the acceleration function. E to the -3, that's a positive value. And then we get 9 minus 12 plus 2, that's going to be -1. So I'm getting a negative negative acceleration. Therefore, velocity is decreasing. My reasoning is because my acceleration is less than 0. Okay, part D, is the particle speed increasing or decreasing? How do we approach that?
See if velocity and acceleration have the same sign.
That's right. Compare signs. Compare signs. I'm sorry?
Is it increasing?
You mean for part D?
Yeah.
Yeah. Speed is increasing for part D, yes, because velocity and acceleration are both negative. They're both. So if I plug 3 into my velocity function, I'm going to get a negative number. Comparing my velocity and acceleration, they have the same sign. Speed is therefore increasing. But if one is positive and the other is negative, then we have decreasing speed. Okay, questions there? Okay, moving on to number 2. Okay, find the derivative for y is equal to 3 minus 5x raised to the 2 to the x. All right, so what do you notice that is different about this problem? Okay, the thing that should stand out is that we don't have a derivative rule that can handle this specific scenario. We have a variable expression raised to a variable expression. Okay. If it's all right, so just as a recap here, if I have a variable raised to a constant, then I use power rule. Okay. If I have a constant raised to a variable, then that's either then I have to use base a. I have to use natural log of a times a to the u times u prime. But if I have a variable raised to a variable, we have to find a way to represent that in a different form. And the way we do that is we do log differentiation. We introduce logs to both sides of the equation. Okay, so everybody see the distinction here between these 3 types here? They all look similar, but we approach them differently. So natural log of both sides first.
Michigan, could you go back to that for a sec? I was just writing.
Yeah, this one here.
So for that log differentiation, is that x is it 5? Is it 5x or 5 to the x?
This one is 5x, but this one is 2 to the x. But either way, these are both. We can think of both of these as variable representations. Right? Okay. There's variables involved in their respective regions. But here, right, this is purely constant. That's purely variable. Oh, sorry, that's purely constant. And well, if there's any variable involved, we call that a variable expression. But this is purely a constant. Right? Okay. So I take the natural log of both sides, and what's the purpose of this? What can we achieve because of our natural log on both sides? What does this allow us to do? Say it again? Oh, okay. Right, bring the 2 to the x down, right? Yeah. And the purpose of that is, well, now we have an easier form to work with. Right? No longer do we have a rule that we can't find, but now we have something that is more manageable, right? Okay, what's next?
Power rule.
I don't think we have power rule here. First off, what happens on the left side? We got implicit, right? Natural log of y becomes 1 over y dy dx, right? And then over here, we have to involve what? How many expressions do you see? 2, right? Got to do the product rule. F prime g plus fg prime. So 2 to the x, we have to apply our rule for a to the u. And then ln of u, we apply that rule as well. So we're going to apply this rule here. And then we'll apply this rule here. Okay, f prime. 2 to the x becomes natural log of 2 times 2 to the x times 1. The original g function, no changes. Back to f. And then g prime. So g prime is u prime over u. So negative 5 over 3 minus 5x. Questions?
I have a question on that prime.
So we're just following this rule here.
Oh.
Right. That's 2 is my a value, and then u is the x. We're just following whatever the rule says.
So the d over dx doesn't really matter.
D over dx just means find the derivative of this is this.
Oh, okay.
Yeah, d over dx just means find the derivative. Okay, so we're almost there. I mean, we have the derivative. That's all taken care of. We just have to, what do we want to get by itself? Yeah, dy dx. So how do we do that? Multiply both sides by y. And then there's one more thing we can do, one more substitution that we can make. Is there any way for me to represent my derivative just in terms of x?
Substitute y for what y was equal to.
There we go, right? If we start with a function, we should be able to represent our derivative in terms of just x, right? We shouldn't have to, the y is just kind of a placeholder until we have our final result. Okay, any questions with 2? Okay, number 3.
Where did you put the 3 minus 5x out of the parentheses?
Oh, from here to here, you mean?
No, from the very last one. The 3 minus 5x in front.
Oh, this one here.
Yeah.
Oh, this one here.
Yeah.
Where did that come from?
Yeah.
So I want to replace y,
Oh, okay.
and y is the original equation. Yeah.
Mr. Yang, how much simplifying are we gonna have to do on the actual test? Like, what would be like an acceptable answer?
Yeah. I wouldn't worry about simplifying. I just like to get things cleaned up, but If everything is there, that's good, right? Because
Yeah.
that's you have the derivative. I'm not going to be picky about how you represent the derivative, as long as everything is there.
Okay, like if it's like a fraction underneath a fraction, would
That's
that
fine.
be okay to
That's
leave?
fine. There's no common denominators needed. I mean, yeah.
All right, cool.
Yeah. So you could have left it in this form if you want, but I do want to see all the pieces in
Okay.
place.
I got you.
Okay, are we good with 2?
Which form could we have left it in?
You could have had this times that. I just like to clean things up a little bit, but you could have had this. I mean, this is the same thing as this, right?
Oh, okay.
Right. These are the same, but I do need to see this piece in front. Okay, number 3. Okay, find y prime. We have a log expression. We're asked to find the derivative, but should we jump into derivative initially? Okay, what should we do? Expand. Yeah. Combination of product and quotient property. Basically, what's going to happen is your numerator is going to be part of a positive log term, and then you see these denominator terms. These are going to end up being part of negative log terms. Right? But as you expand, the 3 is going to tag along in front of each term. Okay, what's next? What can we do next? Can we? Yeah, we can bring the 1/2 down in front, multiply it with the 3. I'm going to choose to leave the 2x up here, but if you want to bring the 2x down, you can do that. I'll show both variations, but right now I'm going to leave that 2x up. Okay, so now we can approach each with our derivative rule, log base a of u. Okay, so let me go through this here. Log base a of u, my a for all these terms is 7, so 1 over natural log of 7. U prime over u, so times 1 over x. Coefficient stays, 1 over ln of 7. And then u prime over u, my rule for e to the u is e to the u times u prime. So e to the 2x times 2 all over e to the 2x. Take out the e to the 2x out. I just combine these fractions here, 1 over ln of 7, u prime over u.
Why did you divide by e to the 2x?
The reason why is because I'm inside a log expression. So I have to finish my rule, right? The rest of my rule is u prime over u. So I have that u prime over u here. Okay, any questions about if you want to bring the 2x down, this is what it would look like. It looks a little bit different, but the answer means the same thing. If you want to bring the 2x down, then it'll become 6x, and then you'll be left with log base 7e. Now, 6 log base 7e, you can put that together. That's just the coefficient from the x. So the derivative of that is just going to be the coefficient in front, 6 log base 7 of e. And 6 log base 7 of e is the same thing as 6 over natural log of 7. So answer looks a little bit different, but represents the same thing, if you want to do it that way. Okay, any questions with 3? Okay, number 4. Quite a few things going on here. What do you guys see? What's involved here? Implicit, a bunch of y's, right? A bunch of y's. We know we got to keep track of some dy dx's. What else?
There's product rule.
Yeah, there's product rule, right? We got to make sure we can spot that, right? 3x squared y. And then what should we do before we start our derivative process? Yeah, see that, right? We don't want to prefer not to find a derivative in this form, right? Prefer to find a derivative of kind of these separate, smaller terms. Yeah, so let's expand first. So I separated my natural log terms, but I can do a little bit more within each term, right? I can bring those exponents down, convert radical to rationals. So I'm just working with my left side here, trying to get it all spaced out. Okay, so I should be able to get all the way down to this point before I think about derivative. Okay, any questions up to this point? Okay, u prime over u prime over u, power rule, and the product rule here. All right. Okay, how many y's do you see? 3. So what does that mean? The next step, we should see how many what?
3
dy dx's. Okay, so 3y's means you're going to produce 3 dy dx's. That's a good way to kind of make sure that you don't have too many or you don't have enough. Okay. All right, so u prime over u, 1 over y dy dx. U prime over u, 1 over x. F prime 3x squared becomes 6x times g plus f g prime. Y's derivative is 1 dy dx. And there's a minus y here. Minus y is going to turn into minus 1 dy dx. I like to have that 1 there. It's a good placeholder. Later on, when you want to factor dy dx out, having that 1 there kind of reminds us that there's something there, that we don't want to just completely miss the fact that there's a term there that remains. 5x becomes 5, constant goes to 0, right? 3 goes to 0. Okay, 1, 2, 3. I have 3 dy dx's. Yeah.
Where do you get the 1 over y?
The 1 over y, so this came from my rule for natural log. So think of y as your u value, right? The derivative of y is 1, so 1 over y. And then we need dy dx because we're asking for y's derivative. Okay, so good with the calculus step. So now we're just rearranging, right? Now we want all the dy dx terms on the left, the non-dy dx on the right, factor, divide over, and then you can leave your answer in unsimplified complex fraction, that's fine. Okay, any questions with 4? Okay, number 5. Okay, find tangent line equation. Okay, so what do we need to do first?
Plug in.
Well, if we plug in, we'll get 0. So we already have the order pair, so I think we're good. But yeah, if I only give you the x value, then you would plug in to find the y value. But we already have order pair, so that's good. Okay, what's our next step?
Find the derivative.
Yeah, find the derivative. And what do you have to involve here? Besides these rules that we have to use.
Product rule.
Yeah, product rule, right? F prime g plus f g prime. E to the u times u prime. Keep the g, keep the f. G prime, u prime over u. Okay, now what can we do with our derivative? Use this to find the what? Slope, right? And how do you find slope?
Use the formula.
Yeah. Well, what do you mean by that?
Y1.
Right, but we need to find the slope, right? That's our tangent line equation, right? But how do we find the slope value? Plug in the 1 into the derivative, right? This is our slope formula, so plug in the 1 to get the slope. And then point slope. Okay, so this is not on the morning review, but this is on yesterday's worksheet that I went over. Being able to find the derivative of inverse at a point. First thing we do is recognizing the fact that the number given to you is not the x value of the function. It's the x value of the inverse, but it's really the y value of the original. So we have to understand that this 2 is going to go into that y location of my function, and we'll have to work backwards to find the x. Okay, so we set 2 equal to the function. This is not going to be factorable. I'm going to have to go through a series of guess and check, but it should be an easy number to find. I like to set equal to 0. It makes it easier for me to find the number. So try 0. 0 doesn't work. Try 1. 1 works. But if 1 doesn't work, then try a few numbers more. It'll be easy. It'll be a small number, easy, close to 0. Okay, so x equals 1. 1 works.
So it doesn't matter what's like set it equal to.
It doesn't matter. Yeah, I mean, you could have found it at this point if you wanted to.
Oh.
Right? Yeah, as long as you just make sure that both sides are equal.
Set equal to 0, so it's easier.
Yeah, yeah, but either way, it's probably same difficulty.
Wait, why did you put? Oh, okay, got it.
Okay, next step, we want to find the derivative of our function. Okay, what's our derivative?
3x squared plus 2.
Mm-hmm. What can we do with the derivative now?
Plug the 1.
Mm-hmm. Plug 1 in, and that'll get us the slope, right? Oops, 1 squared. Okay, so is that our answer here? It's going to be reciprocal, right? So this is the slope of the f graph, but it's asking for the slope of the inverse at its corresponding point. And the relationship of these two steepness is that one's going to be a number, the other's going to be the reciprocal of it. And to give you a visual representation of what we kind of achieved here. Okay. If two corresponding points on a function in inverse are in these locations, then the slope of one, you can kind of convince yourself, right, that they're both positive slopes, but one's going to be steeper than the other, and they're going to be reciprocals of each other. So if this is slope 5, then this is going to be slope 1/5. That's that connection between these 2 points. Okay. Any other questions? I didn't do a curve sketching. Well, I didn't do a first derivative concavity one. We've done that every day. So you guys hopefully have your notes ready and understand that process. All right, first period needs to get ready for their test. But I'll hang around if you have any questions for me.
Thanks, Mr. Yang.
All right, see you guys.
Thank you.
See you.
Thank you.
I couldn't find yesterday the paper with all the, not formulas, but like properties. But my friend
Bye, see you.
just sent me a picture that he found it.
Uh-huh.
Can I use the picture or do you want me to write it down?
That's fine.
Can I
Yeah, you can use that.
Okay. Can I use your service charger?
Huh?
Can I charge it?
Yeah.
Thank you.
Do you have one at home though, Ethan?
Oh, yeah.
Okay, yeah, just bring it. Yeah, bring it.
I remember you going over yesterday.
Okay. Good.
So It was good to hear him again.
Yeah. Good.
I felt like I printed out like all of the worksheets that you recommended, like the mistake.
Yeah.
All that.
Good.
Hopefully less pages.
Yeah. Yeah. And it was also one of those things where if you spend too much time looking through, you're not going to have enough time.
Because
So.
you're like busy, like, is this
Right.
the
Right.
page?
Right.
Oh, like everything's on. They are, you're like, oh, this part.
So.
More fast pace.